Welcome to part 9. When I started this, I never thought it would take this many videos just to build a circuit with a working 8086. However, we have the two EPROMs and the test code loaded across both EPROMs. So I have a working 8086 circuit and I just need to connect this LCD display and then start writing the assembler code for my hello world. I have the EPROM mapped to address 8000 to FFFF, and this was achieved by adding this NAND gate and connecting the 8086 16th address to the chip enable on both EPROMs. Therefore, when this A15 line goes high, it enables via the NAND logic the EPROM, and thus the EPROM responds to addresses in the range 8000 to FFFF. For this 8086 breadboard circuit, we're restricting ourselves to one 64K block. So we have addresses 0000 to 8000 available. My intention is to add the LCD and in a similar fashion to the EPROM enable this LCD display. Unfortunately, it's not that easy. Looking at the LCD display, it has 16 inputs. 8 are D0 to D7. Of the remaining 8, 4 are power and 1 is brightness. So that leaves 3, and these 3 are the RS, RW and E. RS is a register, RW is read-write, and E unfortunately isn't enable. So we'll need to look further at this datasheet to see how the thing operates. This is the LCD datasheet, and as we've established, we have 3 pins, and somehow we need to make this LCD respond. And we've discovered, unlike the EPROM with an enable pin, this doesn't exist on the LCD, so somehow we have to use these 3 remaining pins of RS, RW and E. So let's look further at the LCD datasheet. On page 8, RW is read-write, so we can read or write to this LCD. We aren't ever going to read, only write hello world. So all we can do with this is set it to write. So we'll set this pin low. So that's not going to work as some enable feature. Now looking at RS and E, we can see it says it selects registers 0 for instruction and 1 for data. And if we go to the block diagram, we can see the 2 registers, the instruction register and the data register. And setting this RS pin to 0 selects the instruction register, and setting it to 1 selects the data register. Page 9 provides more information on these registers, and page 24 shows commands to initialize the display, such as switching it on, setting the number of lines, the cursor flashing, etc. Turning back to page 9 and looking at the block diagram, it provides more information that when RS pin is 1, the data register is selected, and it's then that it starts accepting writing characters to the data register, which is then displayed. So there's 2 modes, when we first initialize the display, and then a second mode where we write characters to the display. So we need to somehow program this RS pin to be 0, and then we want to write characters to set it to 1. Page 32 shows an interface example for using an I/O port, and page 40 shows typical instructions. So for example, the display on/off is achieved by setting on the data lines DB3, DB2 and DB1, making those high. And if we look at the timing diagram on page 32, we can see that this is enabled by using the E pin going high or low. So we can see the command on the data line is actually triggered by this E pin going high then low. So we must provide a signal that goes high and low, and this effectively tells the display to execute the instruction that's sitting on the data lines. Similarly, when RS is 1, the value on the data lines is executed by the display, only when pin E goes high and low. Page 32 shows an interface example using this I/O port, and page 40 shows the typical instructions. So we now have the detail on how to get this LCD display to work. We need to set RS high or low, set the instructions on D0 to D7, and provide a toggle of high to low on pin E. It also states that we need to use an I/O port, and it doesn't operate in the same way that an enable pin would work. So we need to see how can we actually get this circuit to work within the LCD. Now, referencing the 8086 datasheets on I/O, it has a section I/O addressing, and it says the 8086 can address up to 64K I/O byte registers, and that means that we can have 64,000 I/O ports or byte registers. Here it refers to I/O ports addressed in the same manner as memory locations. So I'm going to use two I/O ports, 0 and 16. 16 in hex is 10. The 8086 I/O instruction is out, which we used in our test data in the last video. So I'm going to use this out instruction as part of the coding to write to this LCD display. Now we'll look further at the I/O instructions on the 8086. But before that, I was asked about the jump test code in the last video. Here we had a jump back and then a small loop using the jump. And here we see the 8086 starting at the location FFF0. It then goes on to FF2 and then moves on to FF4, and then it jumps to this location F7EA. So that's the larger jump where it jumps to F7EA. Then it jumps to F7EC, F7EE, F7F0, F7F2, and that's the out statement where it's putting the 0 out. It then moves on to FF74. You'll see here that that's what I was asked. It's showing 7 rather than F. And here again, it's showing 7 rather than F. And what we're using is we're using this Arduino sketch, and the Arduino is basically looping round whenever the ALE signal is rising. So it triggers on that rising edge of the ALE, and it loops around here, reading all the 16 address pins. And it's actually going a little bit wrong here. You can see all these are FFFFF. It's showing 7 here, and that's just due to the failure of the Arduino code. It's not actually reading this fast enough to actually interpret the value as and reading that top bit, so it reads it as an F. So although it says 7 there, and although it's not showing that first one, that's really a failure of the Arduino sketch not really being able to read all the pins. So that actually should show F. It's just the failure of this Arduino code. If it did show 7, then the next line would actually be 7, but it's not. It's actually showing F7EC, F7. So the 7 there is just a failure of this sketch not being able to work right. In reality, we use an ICE. ICE stands for in-circuit emulator. So what we could do is we could use that in-circuit emulator to emulate the 8086 and step through using that. But it costs thousands, and Arduino is, a couple of pounds. And so that's why I was using the Arduino. But it's not, it's not exact, and that's why we're saying that 7 there. That should actually be an F. And you can see the F is all it's been able to read it all the way through there. But for some reason, the Arduino is just missing that last one out. It's not been able to read that most significant bit there. And occasionally it's translating that into a 7, where it actually is an F. You see there, it's got it right there all the way through, and then it's gone wrong. Anyway, just thought I'd want to clear that up. Now let's go back to our I/O. What we've learned from the datasheet is there's no similar feature to the chip enable on the EPROM. So we can't use the memory map or code the LCD display to use addresses like 6000. So we're using the feature of the 8086 to perform I/O operation, and we're using a port and an out instruction. We're going to create 2 ports, 0 and 16. 16 in hex is 10. Port 0 using the 8 bits is all zeros, and port 10 in hex is 0001 0000. We then use the AL register in combination with the out instruction. we can set the LCD command into the AL register using the move instruction, and then write out to the content of the AL register to the IO port using the out instruction. We found that the LCD operates by placing a data on its 8 data lines, but that isn't accepted by the LCD until the E pin is taken high and low. So where we've been used to using the read pin on the 8086 as it reads from the EPROM, we're now writing, not reading. And this write writes data out on its 8 data lines. When the 8086 performs a write instruction, the write pin goes low, and on completion it returns to high. So when the 8086 executes the out instruction, it will then go low and then go high once it's completed that instruction. The LCD requires a low then high. So if we invert this write signal from the 8086, we have the perfect signal input for the E pin on the LCD. In addition, not only does the 8086 perform a write, but it also executes an IO command, and so this drives the IO pin low when using the out IO instruction. We also need a way to drive the LCD RS pin from a 0 to a 1. So we can use this IO port, and specifically this 5th address here, which will go from 0 to 1. And we can change the port from 0 to 1, 0. So if we connect RS to this 5th address, we can have this go from 0 to 1. Therefore, we have all signal pin connections sorted. However, it's not unusual for this 5th address to be output as part of a normal command. Quite often this 5th address line will somehow be used to address the EPROM, so we must somehow ensure we only reference this 5th address line when using the IO instruction. So we will add an additional logic gate, an AND gate. And if we connect this 5th address line, which is A4, to the AND, and we use the IO, which we're going to invert because we know the IO goes low, and if we invert that, that goes high, then that means that when IO is high and A4 is high, only then will RS go high. This ensures that any other indication of the 5th address going high, it's not used unless we have an IO instruction too. So what we're going to do is going to connect the NAND gate from the write signal, and we're going to invert that so we can get this signal on the E pin to go high and then low. We're going to use the IO, which will also go low, and we're going to invert that to a high, and we're going to connect to the 5th address line, which is A4, and only then when the IO is high and A4 is high will the RS go high. So therefore we have all the pins connected. The E, which is going to toggle going high and then low, the RS, which we're going to drive from this set of logic, and the data lines we're going to use from the write. The read-write, we're never going to read from the LCD, we're only ever going to write to the LCD, so we're just going to hold that pin low. And so in the next video, we're going to connect all that logic on our breadboard. So first I'm going to add this NAND gate to the circuit board, and then we'll connect that up. Here I have the datasheet for the 4-input NAND gate. What we're going to do is connect that just into here on the board. And then we'll connect up the power. But the connection signals from my LCD for the positive and negative are sort of in the way a little bit, so I'm just going to push these over out of the way underneath the board, just so we can get at the pins easier. Now I'm just going to connect up the power, which is ground is pin 7 and positive is pin 14. Now we've already got the ground going to this pin on the LCD, so we've got ground going to there, so we can just simply connect that across to there to connect that to ground. And then the positive on pin 14. We'll just connect in here. And I'm going to use these pins on the AND gate. The AND is where if both inputs are 0, it's a 0. And if it's 0, 1, it's a 0. And it's 1 or 0, it's 0. So it's only when both inputs are 1 is the output 1. So we're going to use the I/O output of the 8086 into one end of the AND gate, and we're going to actually use the fifth address from this latch into the AND gate. So I'm going to use pins 10, 9 and 8. So let's connect first we need to take the I/O from the 8086 and we need to invert that because it goes low, we need a high. So the I/O is pin 28. We need to connect from pin 28 across and onto the NAND. And here we have the NAND, and we want to connect to the NAND, and we're going to use these outputs here of 4, 5 and 6 on the NAND gate. So pin 28, 20, let's see if we can push it through here. And if we can go to 28, so it's 21, 22, 23, 24, 25, 26, 27, 28. Okay, so pin 28, I'm going to connect that to the NAND, and that's going to be pin 4. 1, 2, 3, 4. One, 22, 23, 24, 25, 26, 27, 28. Yeah, it's 28 through to the NAND. And then the other side of the NAND is going to come out on pin 6. And that's going to go through into our AND gate. So that'll be here, pin 6. So that's the output of the AND gate on pin 6, or on the NAND gate, sorry. Yes, pin 6, the output of the NAND gate, going through to pin 9 on the AND gate. We need to then connect the address on here, the fifth address. So here the fifth address is 1, 2, 3, 4, 5, so it's pin 12 on this latch. So pin 12 is 11, 12, so it's in there. Pin 12, and that will go through perfectly. Oops. Okay, so that's pin 12, goes through to the AND gate, and that's pin 10 and 9 connected, and we then have the output on pin 8, and that will go to the RS pin. So here we have the RS and the output of the AND. So now when I/O goes low, it's inverted by the NAND, which is then goes into the AND gate, and only when both of those, the address coming from the latch, which is the fifth address, and the I/O signal coming from the NAND, which is inverted, will go to the AND gate, and only when those are both 1 will this inverted. Now I need to connect those pins on that NAND gate, because to invert that, we need to connect pins 9 and 10 together, so the inputs go in 10 and 9. and that will invert that, so I need a little jumper to go across there. And that will connect pins 10. That will connect, sorry, on the NAND. We need to connect those two pins, which are 4 and 5. So now it comes in through, goes into pins 4 and 5, and the output comes from pin 6. And that's the AND connected. Next is the E signal, which we need our pulse going high and then low onto the E, which then will activate the data sitting on the data lines in the LCD. So that's going to be the right, which is pin 29, so just one up from our I/O. And we need to bring that into the NAND so we can invert it. And then from the inverted signal, we can then drive into the E. So we need to connect it to these, to this NAND gate on here. So let's see if we can get this wire through here. Okay, and connect that into our right from the 8086 and through across and into our AND. So there we are, the connection into the NAND. We'll need, and that's pin 12. We need to connect 13 and 12 together. And then take the output, which is going to be pin 11, and connect that into E. So there's our E connection there, and our output there. So that's now the right signal going into the NAND gate, going onto pins 12 and 13, so it will be inverted. It then comes out from pin 11, comes all the way through and onto E. So that's our E signal connected. And finally, we have our RW read write, and as we're only going to ever write to the LCD, we're just going to connect that directly to ground. So that's the read write. So that's all the signals of the read write connected to ground, the E signal coming from the inverted NAND, and the write signal, and we're ensuring then the 5th address coming from the latch, and the I/O command coming from the 8086, which is inverted, coming in through this AND gate and onto the RS. And so that's all the signals connected. Next, I need to connect the data lines D0 to D7 to the data lines on the 8086. One thing just to note, you may have seen that I've tried to leave some spaces. So when I was connecting the data lines into here, I could have connected into the here, or when I was connecting the address lines and data lines across onto the EPROM here, I tended to try to leave a space, and I could have used those ones. But the reason why I've left these sort of spaces here is so that when it comes to the Arduino, and when I have to be able to connect the Arduino to connect to the pins, I needed somewhere to be able to connect them in. And if I'd filled in those pins and then tried to connect the Arduino to read these address lines, which are coming from the latch, there's obviously no way I can get them in to connect onto the latch. It allows me still the space to get those lines connected into there. And that's why you'll see that I'm not filling up some of these lines that I could, and here that I could. And that's the reason why I'm doing that. So now we need to connect the data lines from the 8086, and the data lines are 1 all the way through to 7 there, which will connect to D0 through to 7 there. So I think what we'll start with is 0, 1 and 2, which is 16, 15, 14 on the 86. So that's the 86 there, and that's the 3 lines there. So if we connect those first, so that should be the D0 to D0, coming through like that, the D1 through to D1, like that, the D3 coming across to D3, like so. Now we need to connect the next D4, D5, D6 and D7. Now what I'm going to do is I'm going to take them from here. What we have on the EPROM here is 3, 4, 5, 6 and 7. So I'm just going to connect them across from there. So if I connect 3 to 3 over here, so 3 across to 3 on here, then 4 to 4, 5 across to 5, 6 across to 6, and then the last D7 line across to D7. So that's the data lines from the 8086 all across to the data lines on the breadboard. So that's the data lines connected, that's the RS connected, the E connected, the RW connected, and the power and the anodes. So that should be the circuit completed. All we need to now is to write the code, to write the code to the LCD, and we'll go on from there. Finally, now that we have the board all connected and the circuit complete, I just want to power this up to make sure this works. So I'll bring in our clock board and reset circuit, connect the power on here to the rails. And just make sure this LCD lights up. Yep, so everything seems good. The LCD is lit up. We can adjust the contrast by adjusting the little resistor there, so I can turn that to change that. So there we can make it darker, whatever. And so in the next video, we'll be going on to write assembler code and use a compiler. So rather than us actually manually putting in the machine code, we're going to write assembler. We're going to use a compiler that to then generate the machine code and then load the machine code to write the hello world program into the 2 EPROMs now that the circuit's complete. So join me in part 10. Thank you.